Hi everyone, welcome back. We are here to learn about the associative property. So this is kind of a hard one, but we'll get it. You can either call it the associative property, like the associative property, or you could also say a sh sound in there, associative property. And you hear both of those. Now, let's think about part of that word and see if we know what it means. So the associative property, notice part of that word sounds a lot like associate or associate. Well, that's important to help us remember what the associative property does. So the question is, who do you associate with? Have you heard that word before, who you associate with? Well, that means kind of who do you hang out with? Who do you spend time with? Who do you go around with? That's a way we can remember the associative property and what it can do for us and how we can use it in math. So here we have three friends. These three friends all want to go and walk to school together. So the question is if this one walks along and then meets up with this one, and then the two of them walk along and pick up the third, who gets to school? Well, I hope you're saying all of them. They all get to school. You're right. That's exactly right. So let's think about this. I got to find my markers. Let's think about this in terms of the associative property. Okay, so we said we could start with our purple friend. So our purple friend is walking along. Then they pick up the red friend. And the two of them are walking along together. And then finally they go over and pick up their blue friend, and now they're all walking to school. But what if some morning our purple friend comes out, walks to our red friend's house, they're not quite ready. That'll happen. So they say, no worries, I'll go pick up our blue friend, we'll come back and pick you up, and then we'll all go. So our purple friend comes out, walks over and picks up our blue friend. Then our red friend is ready, so they pick up our red friend, and they continue to school. Who gets to school? Everybody does. What if one day our purple friend is having a rotten day, just a hard time, it's gonna be a little bit late. So no worries. Our blue friend says, hey, you know what? You all stop and pick me up every day. Well, I'll just come and pick you up someday. So our blue friend starts. Then our blue friend goes and picks up our red friend. And then the two of them go and pick up our purple friend. Oops, purple friend. Now who gets to school? They all do. So that's kind of an essence of what the associative property is. Now it can work for addition and it can work for multiplication, which is cool. And we'll see what those look like actually in numbers in just a second. But it's the idea that these three, or it could be four or five, they're all associatives. They're all associates. They're all associating together. And as long as they're all adding, or as long as they're all multiplying, it doesn't matter if this one starts, or this one starts, or this one starts. When they all pick up each other, they all end up at the same place. That's the essence of the associative property. Let's see what that looks like with some materials and also with some numbers. Hold on. All right, let's take a look at the associative property of addition with using some rocks. So if you've been following my videos, you know I love collecting rocks. I have since I was a little kid, and I love all kinds of rocks. Sometimes I like to get ones that are crystals, or ones that are a specific kind of mineral that I've been looking for. But you also probably know that ones that are just especially smooth and round, or smooth and oval and flat, things that are just such a perfect shape. I love those too. So my family and I, over the weekend, it was lovely weather. We were out looking for rocks and we came across some really great ones. So I collected a bunch of rocks. So let's try out using the associative property with these rocks. So the first, as I was walking along, I found three rocks that I liked and collected. There they are. So I started out with three rocks. Then as I went along a little further, I got 4 more rocks. There they are. And oops, that one's a little hard to see. Let's switch that one out there. That's easier. Then, as we kept walking, we came upon 5 more rocks that we wanted to collect. So there they are. So it started with 3, then I got 4 more, and then 5 more. So then the question would be, how many rocks do I have at the end of my walk? Well, I started with 3, then I added 4 more. How many do I have now? Well, you probably know a fact, 3 plus 4. You probably know, I have 7. Then, as I kept going, I got 5 more. How many do I have now? Well, you might know a fact as well. You might know 7 plus 5. You might know that that's 12. So I started out with 3. I added 4. Then I added 5. And I have 12 rocks. So let's pause and write that. But what if that's not how I collected them? What if, instead of collecting them like that, what if I started out collecting 4? What if the first, as I walked along, what if I first found 4? And then, what if I found 5 more and collected those? So what if I put that 4 and 5 together? How many would that be? 9. So what if then I collected 3 more? Would it be the same answer? It would. Now you might have noticed in that example I actually used the commutative property as well. What if I didn't use the commutative property? What if I said I wanted to add up the ones I collected second and third? I wanted to add those up first, collect 9, and then I wanted to add them to what I already collected. I collected 3, and then I added 9. Is that the same? It is the same. That's the associative property. It says I could also, I could do those parts first. I could add the 4 and the 5 first. How does this make sense with what we just talked about with the associative property on the board? Well, those 2 friends could have gotten together first, and then the first friend could have gone and picked them both up together. They still would have all gotten to school. So here's the first friend. In this example, here's the first friend. They go and pick up the second friend, then they go and pick up the third friend. But in this example, using the associative property, there's the first friend. The second 2 friends have already gotten together. So the first friend goes and picks up the other 2 that are already together and picks them up. And the answer is still 12. Now I could reassociate them one more way. The tricky thing about this, in order for me to show you this, I also have to use the commutative property. If you haven't watched that video and you're not sure what the commutative property is, please pause this one, go and watch the commutative property one, and then come back. Because the commutative property one says that we can flip 2 numbers around when we're adding or subtracting and get the same answer. So what I'm actually going to do here is I'm going to take the 5 and the 4, and I'm going to use the commutative property to flip them around. Instead of 4 plus 5, I'm going to flip them around to be 5 plus 4. So that's actually using the commutative property. But once I do that, now I can use another example of the associative property. Before, I just added 3, 4, 5. Now, since I commuted them, now I can add the 3 plus the 5 first. What's 3 plus 5? Well, you probably know that's 8. Then once I have 8, then I can add the other 4. 8 plus 4 is 12. So the associative property oftentimes comes into use along with the commutative property. So that's tricky and makes it a little trickier than the commutative to understand, because it's actually this one has to use the commutative property. This one Remember when I first showed you, I automatically did it, and then I backed up and said, wait a minute, I want to try to show you without using the commutative property. But the associative property is who associates with whom. And as long as they are all addition in there, they can associate in any way, and you still, as you see, come out with the same answer. Let's try that in another way. All right. Now, we don't actually want to build this one out, do we? I don't want to build out 83 rocks and then another 19 rocks and then another 17 rocks. That would kind of be insanity. So instead, we want to see, can we use the associative property without modeling it out? Can we use it when we're just talking about numbers? And the answer is yes. Yes, we can. Now, if we had been collecting and collecting and collecting, maybe I took all of the rocks I collected from my childhood, 83, all through my childhood, I collected 83 rocks that I wanted to keep. Then one year, my family and I went out and collected 19. And then another year, my family and I went out and collected 17 more. And we said, with all of these rocks, how many do we have now? And we wanted to add them up. So you could just add them straight up, line them up with the tens place and a tens column in the 10, all the things in the tens place in the tens column, all the numbers in the ones place in the ones column. You can add them up just like that. But the associative property tells us that it can help us sometimes, especially in mental math, but even when we're doing it on paper. Now, let's take a look. 83, 17. I noticed something about 83 and 17. Do you notice anything about those numbers? Well, I know that 3 and 7 make a 10. And I'm really great at adding tens, especially in my head. So what if we commuted those two numbers, 19 and 17, so that then we could associate the 83 and the 17 together before we did the rest of the problem? What would happen if we did that? Let's take a look. Together, plus 19, 83 plus 17 plus 19, 83 plus 17 is 100. So now I've got 100 plus 19. Well, I can do that in my head, and I bet you can too. 119. Now, you might have said, oh, well, okay, but I'm really good at doing this. I'm really good at doing 83 plus 19 plus 17 and finding the answer. And if you are, awesome, good for you. But what you've heard me say probably before, and what you'll hear me say again is, no sports team only wants to have one play. They always want to have more, because one play is awesome and works really well in some situations, but not so well in others. Plus, your opponent is going to know exactly what's coming after the first time you use the play. And then they say, oh, okay. The second time they're like, oh, that was weird. Used the same play, but okay, trying to trick us. After the third play, they're going to go, all right, well, that's easy to block, or that's easy to shut down in some way. And pretty soon, you're not going to ever win a game. In fact, what if you only had an offensive play? What would you do on defense? If you only had a defensive play, what would you do on offense? So the tricky thing about game playing sports is you need to have many, many, many plays, often to kind of accomplish the same goal, but you have to do it in different ways. Well, guess what? Math is the same. If you have many strategies of how to get something, how to solve a problem, then you have lots to choose from. And then no matter what kind of a problem it is, you can choose the strategy that's the best, not just the only one you have. So if you have this strategy, fantastic. But don't let having this prevent you from also having this. Make sure you also know the associative property of addition and can use it to your advantage when the time comes. All right, so you might be wondering if the associative property will work on something that's not whole numbers. You might be thinking, well, what about decimals? Does it work on decimals? What about fractions? Well, fractions and decimals, if you remember, are kind of the same thing in that they both show parts of a whole. So when we have $3.38, the $3 is the three whole dollars, and the 38 means 38 pennies out of 100. So it's 38 hundredths. Now, when we're writing money, we write it like this, but we could certainly write it as a fraction as well. As a matter of fact, when we hear how we say it, 38 hundredths, we could write it that exact way, 38 hundredths, 38 out of 100. So that means a part of something, not the whole thing. So the question then is, does the associative property, does it work if we're talking about fractions or decimals? And the answer is yes, it does. So in the commutative property example, I showed you an example of how it works, how the commutative property works with fractions. So here in this video, I'm going to show you how the associative property works with decimals. To do that, I've changed the decimals into money, and I've laid out some money, so let's take a look. Okay, you can see I've got $3.38 plus $4.48 plus $1.52. Now, we could just add those up. First of all, we could sort of add up all the dollars. We just count up all the dollars. Then we could put the coins together. That would be a really great way to do it. In fact, it might be a super successful way to do it. But what if we didn't have all the money laying out, so it wasn't quite so easy to see that that was a choice? You might see it in your mind. You might go, oh, okay, well, I know it's $3 and $4 and $1. Why would I put all those together and get $8? Then you might think of 38 as 1/4, 1 dime, and 3 pennies. You might think of 48 as 1/4, 2 dimes, and 3 pennies. 52 as 2 quarters and 2 pennies. If you did, you might say there's 1/4, 2 quarters, 3 quarters, 4 quarters. There's $1. So you could be taking those things apart and thinking about it. So when you put it back together, it was really easy to think about. But if you didn't have it like sitting here, you might not think to do that. Or that might be hard for you. Let's talk about another way that we can use the associative property. Take a look at these numbers. Are there any that could go together easily and quickly? Well, you might notice that 48 cents and 52 cents go together really, really well. Why do those go together so well? Well, it's because if I took the 2 and stuck it over here, it would be 50 and 50. So those two go together super easily to create $1. But in order to do that, I need to use the associative property. I need to say, I don't have to start with this one. I can start over here. In fact, I don't even have to start with the whole numbers. I could start with the decimals. So if I know that 48 cents and 52 cents together make $1, I've already taken care of that part of the problem. Now I know here's just $4, here's just $1, here's just $1, and now it's $3.38. So I could do 4 plus 1 plus 1, 4, 5, 6. So I have $6 over here. And now my new problem is $3.38 plus $6. Well, that's pretty easy to solve, isn't it? I bet you can solve that without having to do anything aside from mental math. $9.38. Now, you might be thinking, wait a minute, that's not how my teacher told me to add decimals. My teacher told me to always, 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 always line it up, bring it down. And I hope you sang that song with me, and thank you for doing that. You're right, your teacher did teach you that one strategy is to make sure that the decimal places are lined up, to make sure all the ones places are lined up, all the tenths are lined up, all the hundredths are lined up, and that's a really great strategy. But don't let that be your only strategy. If you can use the associative property, You might not even need to line them up and bring them down. You might be able to do it in your head. Let's see what this looks like when we're using multiplication. Okay, let's take a look at how this associative property works when we're multiplying. Now, first of all, you'll notice that the only operation we're doing in here is multiplying. This doesn't apply right now if we had adding and multiplying, or subtracting and multiplying, or if we had parentheses already in there that needed to be solved first, or exponents. So the associative property takes place for multiplication and addition when there's all the same operation going on. So we have 4 times 2 times 9. Now, you've heard me say it before. It's really important in math that you make numbers mean something. Don't just have them be numbers on a paper. It's really hard to think about. Instead, even if you're not given a context, and sometimes we math teachers will do that to you. Sometimes we'll give you a problem like this and say, solve it, and it's just numbers. Then it's up to you to give the context. In this case, I'm going to give you the context. So there's 4 times 2 times 9. Now, first of all, times means, I hope you said groups of. Times means groups of. So 4, groups of 2, groups of 9. That's a little confusing unless you have some context around it. Let's start at the beginning. 4 groups. We need 4 groups of something. So I brought my paper plates to solve it, to kind of spread them out. And I also brought the industrial box of fruit snacks. So if you've been holding out, waiting for the fruit snacks, they're here. So let's get started. Okay, so we've got our 4 plates here. Well, here's the scenario. As you know, I have 4 people in my family, and we all love to go out on nature hikes. So we're all going to go out on a nature hike, and so we're each going to pack our own little snack lunch, and part of that snack is going to be fruit snacks, partly because my boys love them, and partly because works great for math. Double duty. So here are our individual plates that we're going to pack, and then we're each going to take 2 packs of fruit snacks. We've got 4 groups of 2. 4 groups of 2. So we're each going to take 2 sets of fruit snacks. Okay, there we did. So we've all got our 4 groups of 2. There's 4 groups of us. We've each gotten 2 packs of fruit snacks. But there's another part of the problem. What is the other part of the problem? Times 9. Where's that 9 in this example? I hope you're saying there's 9 inside. There's 9 inside this one, 9 inside this one, 9 inside, 9 inside, 9 inside each of them. So we've got 4 groups, 1, 2, 3, 4, of 2, 1, 2, groups of 9, 9, 9, 9, 9. So there we've just modeled it out. Now, you've heard me say this before. Don't just let me sit here and play with math and you watch me. No, go and get something that can help yourself model it out. Doesn't have to be fruit snacks if you don't have any, no big deal. But find something that you can model out 4 groups of. In each of those 4 groups, there's 2 of something. And each of those 2 of something, there's 9 of something. Or a different problem if you want to solve a different problem while we're going along. But don't just watch me play with math. You should be playing with math. It's a lot more fun and better learning. All right, let's see if we can solve this now. Okay, so I can just solve it straight through from left to right. 4 times 2, 4 times 2 is 8. There are 8 packages of fruit snacks. 8 times 9, 8 times 9 is 72. So 8 groups of 9 in each is 72. So that's a great way to solve it. But you may want to switch it around using the associative property, and you can do that. Absolutely. What if you said, you know what? That right there actually is pretty easy. But what if you said, I want to switch it around and I want to have this, I want to do 2 times 9 first because I've got 2 groups of 9 on each plate. So there's 2 groups of 9, 2 groups of 9, etc. What if you said I want to do 4 groups of 2 groups of 9? Could you do that? You could. Now, I'm not as good mentally of saying 4 groups of 18 in this particular problem, but in some problems you'll encounter, it actually makes it easier to do it that way. This time, 4 groups of 18 for me mentally is harder, but 4 groups of 18, it's still 72. So this works. It has the same number of fruit snacks, whether you go straight from left to right or whether you use the associative property. Now, we could also use the commutative property first and switch something around. We could use the commutative property and switch the 2 and 9 around, and then use the associative property and associate 4 times 9, which is 36, times 2. That would be another way we could solve it. We had to first commute it, which is okay too, and then we reassociated it and we still get 72. But no matter how we rearrange these, there's still 72 fruit snacks there. That's the essence of the associative property. All right, let's try one with just numbers. Now, again, I don't want to model this. You don't want to see me model out 26 plates, and each of those plates has 25 fruit snacks on, and then a measly 4 fruit snacks per package. That wouldn't be fun either. So you don't want to see me model this out. So some problems, when we get to some problems that are more difficult, we want to be able to see how this works, even when we're not modeling it out. So 26 times 25. I don't know what that is. Do you? You might know with a calculator, and I might know with a calculator too, or we could do some work on the side. But if we pause and see the whole problem and stop and think to ourselves, could I use the associative property on this problem? It's going to be a lot easier. In fact, it's going to be easier even than tracking down your calculator. 26 times 25 times 4. I see something that's going to make it really easy. Do you notice a part of the problem that's going to make it really easy? I hope you noticed that. What if we skipped over the 26 and we did the 25 times 4 first? What is 25 times 4? I hope you knew it was 100. Now it's super easy. We're awesome with ones. We know the zeros trick. So 26 times 100, 26 times 1 is 26. There's 2 zeros in the problem. That gives us 2 zeros in the answer. So we didn't have to go and find our calculator to do 26 times 25 and then times 4. We could do 26 times 25 times 4 together, which is 100. 2600. That made the problem a lot easier. Let's try one more. What about 8 times 9 times 5? Better for modeling out, but still, can we just do it with mental math using the associative property? Well, 8 times 9 is 72. 72 times 5? Trickier. You might not know that just mentally. So what else could we do? How could we switch this problem around using the associative property? Well, the trick on this one is we first need to use the commutative property. So first, we're going to take 8 times, we're going to switch the 9 and the 5 around using the commutative property. Does that help you figure out how we're going to do it mentally? You bet. We're going to do 8 times 5. 8 times 5 is 40. Now, again, we're awesome with zeros. So you probably know this just in your head. You don't need to either work it out on the side of a paper or get a calculator. 40 times 9? 360. Now, let's pause and try this again with decimals and see if it works with decimals too. Okay, well, I actually changed my mind. I decided it might be harder to understand the associative property with fractions than with decimals, so I wanted to give you a fractions example so we can consider that together. So here's my associative property problem for multiplication. 2/3 times 1/2 times 3/4. Now again, without any context, you think, what is that even about? So here's the context. At my son's school, they have an amazing strings fest where all the string players, violas, violins, cellos, basses, and all of the grades get together and play one big concert. So from grades 4 all the way through 12, they have one big concert. And they call it Strings Fest, and it happens in the spring. It's really amazing. And it's so big that it pretty much covers most of the gym floor in the high school. So there's bleachers on the one side where families sit, there's bleachers on the other, there's bleachers on the other, and then most of the entirety of the floor is covered with strings players or either them, their chairs, their stands, their music instrument cases, whatever it may be. So that's the three-fourths, because this is two-thirds of a group of a half of a group of three-fourths. What that means is we're starting with three-fourths. So the players and the musicians and their equipment and everything takes up three-fourths of the gym floor. So I'm going to pause and draw that out. There it is. Now you might be wondering what they do with the other one-fourth of the floor. Well, the other one-fourth, they sometimes set up chairs for families to sit as well if we ran out of room and all the bleachers around and whatnot. But the conductors also need places to be in. They need places to walk and whatever. So the last fourth of the floor has a combination of chairs for the audience and then also just walking space so everyone can get in and out. Now, this is two-thirds of a half of three-fourths. So, within all of these students, musicians, and all of their equipment, about half of it is made up of fourth and fifth graders, which is really cool because they're starting new instruments. They're just learning how to play their string instruments. And they are about half of the whole entire orchestra, the whole entire Strings Fest. So that's really cool. So let's mark off a half of all of this area. There we go. You can see I actually changed the half to red too so that it matches so it's easier to see. So that area right there on the gym floor is the fourth and fifth graders and their instruments and music stands and everything like that. But there are so many fourth graders. In fact, almost every single fourth grader in the district tries out playing strings, which is so cool. And they get an opportunity to learn how to read music, how to play an instrument to get started with it. It's really, really a neat thing. So two-thirds of that half is fourth graders. That means the other third is fifth graders, which is also really cool. But two-thirds of this area is fourth graders. So we need to mark off two-thirds of this half. Well, we see the denominator is 3, so that means it's cut into 3 chunks. So we need to mark off two-thirds of this area. Let's pause and do that. Okay, so you can see I changed the two-thirds again into green, so it was easier to see on my diagram. So of the half that was fourth and fifth graders, 2 out of 3 pieces you can see this one was already cut. This one half, or this one fourth here, was already cut in half. So I just took the other fourth and cut it in half to make 3 equal pieces that equaled that half, and I chose 2 of them. I chose those 2 in green. So you can see this area right here is all fourth graders. So two-thirds of a half of three-quarters of the gym is taken up by fourth graders. Now, you can see how this could be useful because when the orchestra directors are planning how to set things up, where to put the chairs, where to put the stands and the music and everything, they would know that they needed to have this much for fourth graders, this much for fifth graders, and then this much for 6, 7, 8, 9, 10, 11, 12th graders. So that's kind of useful, isn't it? Now, let's see what is the answer then. Well, we can see that this two-thirds right here, actually, according to the diagram, is really 1 out of the 4 pieces that we started with. So it's 1/4. You could also name it 2. If we cut all these other ones in half again, you could name it 2 out of 8 pieces because it would be 1, 2, 3, 4, 5, 6. We'd cut that one in half. 7, 8. We'd cut that one in half. So you could name it 2/8. But in simpler form, it's 1/4 of the gym floor. So you might be wondering, okay, but how does this show the associative property? Well, we actually used the associative property when we were drawing the picture and puzzling it out. We didn't start with the 2/3, did we? In fact, we didn't even start with the 1/2. We started with the 3/4. Then we did a half a group of 3/4. So we actually did 1/2 times 3/4 to start. We started with that. Then, after that, then we multiplied by 2/3. So we did that part, and then we did 2/3 of a group. So just simply modeling it out, we used the associative property. When you are doing multiplication with fractions, we'll show it what it just looks like with just numbers in a minute, but you see from how we did it that we need the associative property really, really helps us because we used it when we were modeling it. We didn't do 2/3 and then multiply that by a half and then multiply that by 3/4. We started with the 3/4, then we multiplied a half times the 3/4, and then finally we did multiplied 2/3 of what we had before. We couldn't have done that without the associative property. Hold on, we'll try to look at it with just numbers. Okay, last example of the associative property of multiplication. So we got 5/6 times 1/4 times 3/5. Now, let me show you how it works just with the numbers. So if we are working left to right, we would do 5/6 times 1/4. 5 times 1, we know how to multiply. Top times top is top, bottom times bottom is bottom. So numerator times numerator is the numerator. So 5 times 1 is 5. Denominator times denominator is the denominator. So 6 times 4. So we've simplified this part of the problem, and now we're on to the next part of the problem. So now we have 5/24 times 3/5. Well, you could go ahead and simplify, and that would make it easier if you simplified. But if you didn't, or if you forgot, or you didn't know how to do that before you did the rest of the problem, you would do again, top times top is top, numerator times numerator is the new numerator. So 5 times 3 is 15. 24 times 5. Well, that's kind of a tough one. You might know it or you might not, but that's a hard one to do in your head. Now I know it's 120. So our answer is 15 120ths. Of course, we need to reduce that. What would that reduce to? Well, we would divide each, the top and the bottom. They both have 3 as a factor, so we could use 3. So 15 times 3 is 5. 120 times 3 is 40. Is it as low as we can go? Hopefully you know it's not. 5 and 40 both have 5 as a factor. So we can make those numbers lower. 5 divided by 5 is 1. 40 divided by 5 is 8. To get our answer of 1/8. Let's see if the associative property could have helped us. Okay, what if we started by commuting these two numbers? We kept the 5/6, kept the multiplication sign, and commuted those two, 3/5 and 1/4. Again, if you haven't watched the commutative property of multiplication video, go back and do that to understand that. Now, what can we do from there? Now, it's a lot easier to do 5 times 3 is 15, 6 times 5 is 30. We still, if we're not simplifying at the beginning, we still have big numbers, but 15 times 1, well, that's easy. We know that one. 30 times 4, also a lot easier because we know our 3 and 4 facts, and we know how to multiply when there's a 0, multiples of 10. So we know that's 120. So there it is. We've come to the same answer. We still need to simplify, but It was much easier to do in our head. This part of the problem got a little sticky, but we got rid of the stickiness by using the associative property, by reassociating the numbers to be which went first, which went second, which went third. As long as they're all multiplication, we can reassociate them to make the problem easier. I hope this video has been helpful for you. Watch for the next video on the distributive property. Till then, see ya. Bye-bye.